All right. Um, Hello, everybody, and welcome to the August edition of PyData Sofia. Our first online meetup, and for the time being, PyData Sofia will continue being online. If you'd like to check previous talks from our previous meetups, you can check the same channel as is in the stream. And furthermore, I invite you to join our Facebook and Meetup pages to stay updated when will be our next meetup. For now, we're planning to have a meetup probably in second half of September, but we'll see on the exact date. As always, if you have any suggestions for us on how to run these meetups more effectively, please let us know. And more importantly, if you'd like to talk in any of our next meetups, please reach out and we can make it happen. As a reminder, all talks related to Python, R, data science, machine learning, or general software engineering are welcome. We also invite all speakers, regardless of their experience, to join. This is I especially want to emphasize this for more junior folks. Even if this is your first technical talk, please do reach out. We can help you out with some advice on how to prepare your presentation, your slides, and so on. So today we have two talks. First, Rick De Silva will talk about building a serverless computation environment for Python. Following that, Volko will give a talk titled Compact Surjective Encoding Autoencoder for Unsupervised Novelty Detection. That's quite a mouthful. Finally, as always, we'll finish our meetup with a discussion where I invite everyone to join and share their experiences with, let's say, a new Python package, or to share interesting project they've been working on. One thing that we'll do a bit differently this time is that I'll stop the YouTube stream before the group discussion starts, so you can freely join and talk about anything without kind of feeling not confident enough to talk on YouTube stream and having your ideas recorded for for the future. You can just join in and talk about anything you'd like. So we'll start with our talk soon, and if you have any questions to any of the speakers, you can ask them on the YouTube chat, which should be on the right or on the bottom of the stream. Or if you don't want to have a YouTube registration, or you kind of have any other concerns, you can use Slido. The link to the Slido event is shared in the chat, or should be there. Or you can just go to slide.do and you can type the code PyData, and you'll be directed to the question page again. One thing to note about the questions: if you would like to ask something, please include some context in your question. For example, instead of saying "why is that?" or "why do you think so?", please ask "why would you use method X for Y?" or something like that, because we'll be reading out the questions at the end of the talk, and it's a bit hard to get the context at the time of asking. And now, without further ado, the first speaker is Rick, who is a former software and data engineer at CMR Surgical. Now he's fighter at Condense 9, where he makes it easier to build and run serverless systems. Heading over to you.
Awesome. This is really interesting. Speaking at my laptop, and I'm just going to hope that this is all working. I think if anything does break, now George's going to message me or something. Anyway, let's see how it goes. As you said, my background is in robotics, software. I did a little bit of electronics, then moved into software. And the last year I was doing data science and data engineering. And I was building some cloud systems and got frustrated with this project. And that's what I'm going to talk about today. Let me get my screen share on. Right. So that should be good. I think we're working. Yeah, we're working. Great. So what I'm going to show you in the next half an hour is a new way of thinking about cloud computing. And I think that it's important to change the way that we think, or to expand the ways that we think, and like the programming languages that we use or we speak, because they sort of constrain us in the problems that we can solve. And so when you learn a new way of thinking, you kind of gain extra perspective. And you can find that some problems might actually appear really easily when you change the way that you approach them. So that's the kind of core principle behind what I'm doing today. The project is called Teal, and it's open source. It's on GitHub, and really it's a question of how can we go beyond infrastructure when we're building serverless applications. So if you haven't come across serverless, we'll talk quite a lot about it. But it's basically this idea where we can build cloud applications without having to worry about without having to manage the infrastructure that they run on. But though we don't have to manage the infrastructure, we still have to think about it, and we still have to design it, and we still have to. It plays a really big part in the design process of a cloud application now. So we've sort of traded like this operational thing where we get amazing scalability with our applications, but we trade that for development complexity, where we have to spend a lot of time up front designing things, building complicated test frameworks, learning new paradigms and new ways of doing software up front. And I think we can kind of get the best of both worlds. And I think that we can kind of go beyond the thinking about infrastructure where we are now. So I want to be able to build cloud applications without even having to think about infrastructure. So that's my goal. And the best analogy that I can give you right now is to think about compilers and assembly language. Early days of computing, like we used to write software in assembly code, right? And it was very hardware specific for a specific processor, and it took a long time. It was very manual for a long time. And nowadays, no one does that. We use compilers, or we use high-level languages that are cross-platform, in the sense that I can take my Python code and I can run it on computers or operating systems, expect it to work, because there's like a standardized API or application interface that I can depend on. That's what I kind of want for the cloud. I think that a lot of the stuff that we do right now is a bit like assembly, is a bit like wiring stuff together by hand, and I think that should be compiled. A bit more about serverless. I'm really referring to functions as a service, which is like this idea that you can take your little Python function or JavaScript or whatever and go and deploy it in the cloud and attach it to some event that happens in the cloud. And when that event happens or takes place, your code gets run, and you don't get charged if the event doesn't happen. So like that's great. The cloud provider sort of handles all of the scalability. They're really easy to set up. They're configurable. You don't have to manage any infrastructure. It's kind of great. The problem is that lots of these functions, and you end up wanting to break up, because they're such nice building blocks. You want to end up starting to like break things into really small pieces. And so like this is the kind of common pattern where, and it's a good pattern. Like these diagrams are good. Like they kind of make us feel like good engineers because they're complicated and there's lots of colors. They're great because we can feel good about designing these complicated architectures, and we can say, well, we've got our code in 20 different places and it's all decoupled and nice and wonderful, fantastic. But the problem with this kind of this approach to designing systems, software, in the sense that it's not composable. It's not easily abstractable in the sense that, in the way that software is. So you can take your flowchart and you could put it into another box, which great hides the details, but it doesn't let you easily compose it with other boxes. It doesn't really let you define nice interfaces. It's not really software. It's a great way of designing process, but software is much more about data rather than process. So, and then there's like a billion tools that go alongside this kind of design, and because it's all bespoke, you're going to spend ages like setting these things up, and you're going to spend a lot of time and money trying to run them and understand them and figure out how they're doing. So the goal is, well, how can we take this like flowchart design and turn it into something that's a bit more like software? To do that, we're going to look at an example of a pretty simple kind of project, and we'll implement it, or we'll look at implementing it the old way, and then we'll implement it in Teal, and we'll see what happens. And so, like I said, the background of this is data engineering, and you could think of this as a very straightforward like ETL pipeline. You've got steps, data in one end, data, and you get a result at the other end. And maybe there's some stuff that can be parallelized, and you could use a tool like Airflow to do this, but then you're managing infrastructure because you've got to go and deploy an Airflow orchestrator. Use like AWS step functions, but they're expensive, and you're gonna have to write JSON or YAML, and no one really wants to do that. Let's be honest. So the other way that you could do this is you could build this thing manually. So you could say, all right, I've got my three functions, and I will literally just pass my data from one function to the next function and get the result at the end. And that would be fine. That would work a lot of the time, and it would kind of be all right. And you would be able to test each function individually, and you'd be able to maybe use local stack to test everything locally, which is local stack is a tool that simulates an AWS environment on your local machine. So that's kind of good, because now you're like simulating some kind of crazy cloud environment, and it's never going to be perfect. And so you're always going to have to make some kind of staging environment, and CI is great. Like you're always going to have that, but there's this extra complexity because you're going to have to integration test the whole thing in a real cloud environment. So you'll do that, and then you'll realize that the kind of traditional way of doing this right now is to put some kind of queue between each function, some kind of message passing service, so that you can say between each function, right, I'm done now, and the next one can pick up from where I'm done. And you need a way of handling errors, and there are pretty standard ways of doing that, and that's fine. But this is just like extra complexity, and there's a lot of code to write. You're going to spend quite a long time, and you should absolutely be using infrastructure as code to do this, like Terraform. Don't use CloudFormation. Well, maybe you can use CloudFormation if you want to have fun. But anyway, you're going to write a lot of infrastructure as code, and that's kind of scaffolding, really, and it's kind of plumbing. And as a software engineer, I don't really want to spend a lot of my time doing that, especially cross projects. I think that kind of stuff is really just boilerplate, and I should just do it once, or better yet, a compiler should deal with it. So, all right, what did I want from Teal? Coming up with it. Well, I want to use Python, of course, because all my scripts are already written in Python. Python has some excellent libraries for doing data, everything about data, everything data is like Python, fine. There's all this great stuff. So I want to use Python. I want to be able to test my entire application, including the logic locally. And I don't really want to have to simulate AWS to do that. I just want to be able to test the thing locally. Actual debugging. So in your three function pipeline, well, what if the second function fails? I want to be able to see I want to see the stack trace from in the context of those other two functions, and I want to see pass from one function to the next, which doesn't exist at the moment, or it's quite hard to get at the moment. Clearly, I want some kind of operational support. I want to be able to know if it's running and if it's okay. And partly, this isn't as important, but partly in the future, what I really want is to be able to take my application and just run it anywhere, in the same way that I can run Python on a operating system. I just want to take my teal function, my teal program, and just run it anywhere. So let's try it. Let's jump in and see where we get to. Is that working? Yeah, I think we're still good. All right. What have we got? Like I said, Teal's open source, and programming language and kind of virtual machine on top of serverless is the best way to think about it. So there's a runtime, and originally I wanted it to be embedded in Python, and we'll talk more about that later. But I couldn't make that work. So there are semicolons and braces because it makes it easy. Please ignore that and forgive me for the semicolons. Let's do the classic thing. And we'll just say hi. So this is the teal function on the left, and to run that, I do the kind of what you'd expect. And then we get our hi, and it prints it twice because teal CLI prints the last value returned, which isn't really important. Our three Python functions that we talked about, fg and h, they do some maths, and I haven't really checked that maths, it's not important. But they print some messages so that we can see what's going on. And clearly we could go away and unit test these functions and make sure that they work. Fine, not interesting. Let's build our pipeline. And we're going to essentially do the same thing as those three chained lambdas. So to do that, we have to tell teal function lives. And this is a foreign function interface if you've come across that, but it essentially tells the teal compiler how to, and then we'll define our compute pipeline, which does nothing more than call inline, and we'll just test it with something whatever. It's not really important. 1, fine. Okay, great, fine. We've got a result. That is kind of interesting, but all it does is call the functions in line, and it doesn't actually. This actually won't result in 3 separate Lambda functions. So we can deploy this right away to Lambda now. And I'll show this to you again with the verbose flag on, so we can see what happens. This is creating some resources in AWS to go and run our code. But the interesting thing here is that won't change much, which is why it's so fast to deploy. So 6 seconds to deploy, and I can go and change that code, and we will, and it'll be the same speed. So now that it's deployed, we can do teal invoke. And we should get the same result, which was 3. But what I want to point out is that all of this happens in the same thread 0. And on AWS, a thread corresponds to a Lambda function. So that means that all of this is happening in the same Lambda function, which is not what we wanted. We wanted 3 Lambda functions. So the way that we do that is we call the function asynchronously. I'm defining a few helper functions that do nothing more than call the original function asynchronously. Come across async before, it's pretty. Go and run this function. Give me a handle to the result that I can use to check when it's done. And I do that by using await, which says if not, stop completely. And restart when it is done. So it's a bit like an implicit callback. We'll go into a bit more detail about how that works later. And we can run it again. Oh, I didn't mean to do invoke. We need to deploy first. So deploy and invoke, and that should only take a few seconds, like 3 seconds, to go and completely change our Lambda architecture, which is slightly ridiculous compared to doing this the old way. And what we should see is 4 different threads, a bit longer because we've invoked 3 separate Lambda functions. But good, okay. Let's add a little bit more context to see what's going on. So print start and end, deploy and invoke again. And I'm doing this so that I can see what thread 0 is doing, because there's an interesting point that when thread 0 hits this await statement, it completely stops. You're not being charged for idle time in that Lambda. So this is useful if you've got your data pipeline and you break your data into chunks and you want to go and process each chunk, and you want to synchronize and you want to wait until all the chunks are done, but you don't want to have to be continually polling because that costs money. So this just completely stops, and then obviously carries on there and finishes. So let's talk about the case that I just mentioned. Like if we had a bunch of things we wanted to do all at the same time, and we wanted to do it in a cost-effective way. I'm going to copy this in and revert. So same functions, same preface, but what we're doing instead is we're computing 2 separate pipelines at the same time for the results to come back. Thing with the results. We can deploy and invoke that. Normally, I would test this locally first and make sure that but because it's so fast to deploy, I'll just deploy it anyway. Also worth pointing out, if you were to do this using the traditional method on Lambda, you'd have to figure out some way of values. So you probably need several queues, and you need some logic. And it would be awkward and kind of tricky. So a few lines. And that took 10 seconds as expected, because the original one took 10 seconds and we're computing them both at the same time. So it shouldn't take any longer. Great. And we've got 8 threads, which is also, again, what we expected. We could do something more interesting. If we had a list of values, we could map over them, and we could use like a for loop, map in the functional sense. We could just map this function over each of those values, and then we get the result. And we could do it in parallel if we wanted or not. So towards the Spark kind of approach, you describe your transformations in some kind of language, functional language, and then the cluster engine goes away and runs it, except that this is all running on top of Lambda. Do other things that a normal cluster can't, like anything that can trigger Lambda can trigger Teal. This is a common use case where you've got some endpoints, and one of the endpoints takes a long time to compute, and you don't want your front end to be waiting for the results to come back. So you fire up some background task. You would use a job runner like Celery or something, or RabbitMQ, whatever. You would fire off this job to go and run, and your client would then query the state. And in Teal, it's changing a function call to async, which says, well, we'll do this, we'll kick this off, and we'll return a session ID to the user. Okay. Let's deploy it. And Teal handles the API endpoint configuration. I think I've already set, yes, I've already set our API endpoint to an environment variable. That looks correct, which means that I can go and curl say hello. So this is just going to call the on HTTP method. This is like a fixed fixed function. It always gets called when the API endpoint gets hit. So we're getting hello James, great. And we could go and compute. This is the more interesting one. We expect to get a session ID out immediately, which we do, and then we can go and query that and see whether the background is done, which it is. 6 seconds later, great. So then we can go and do what we need to do, and the client never knew the difference, and that saves us the pain of then going to configure some kind of extra infrastructure to do the task management. It's all kind of out of the box and is slow though. So like I would never use this kind of API endpoint for an instant reaction on a web page, but that's just engineering. That'll come. Right, let's back into the slides and recap. See where we got to, because that was a bit of a whirlwind, and yeah, I couldn't cover a lot of things. So we talked about this pipeline thing, which was kind of interesting, not super surprising, but we instantly get logs all aggregated. So we don't have to do any kind of work pulling logs together, which ordinarily we would have to do if we were doing this manually. We looked at parallel computation, and control flow things, which again we can't really easily do if we were doing this traditionally. There would be a whole lot more infrastructure involved. We talked about maps and the functional style, and so this is really kind of starting to get closer to a platform like Spark, where we can write these quite nice programs, but then they just go and run, and we don't have to manage the glue logic of making them run. We talked a little bit about API endpoints, and I think the key point here is that anything that can trigger Lambda can trigger Teal, and it's therefore we've kind of got the whole AWS ecosystem to play with potentially. So making call outs to other AWS services that then return values to Teal is totally possible and is going to come at some point. A bunch of other things I didn't talk about, but more or less what you'd expect in terms of configuring the runtime environments. And Teal does a little bit more to make it easy for you to, for example, trigger file upload processing. So you upload a file to AWS S3, which is an object store, and Teal will automatically pick that up and run a function for you. Totally convenience, not particularly interesting or innovative, but very convenient. So I get a lot, and it's a question I ask myself as well. Why is Teal not a library in Python? Like, why is this a new language that's got semicolons, and I don't want to have to learn a new language, and this sucks, and goodbye. Why is it not just a library? That it was. That's how it started. It began its life as a library with decorators and other hacky things to try and make it feel like Python. But the reason is that await is the logic of await says entirely in the middle of a function. So we're in the middle of main, and we just want to stop running statement. We want to halt the interpreter state to disk, and then pick it up later again. So we're not wasting time and compute resource, and so we're not paying for extra time on Lambda. And I couldn't figure out a way of doing that with pure Python. It felt like a huge task to say pause the interpreter using the Python 3 various approaches like using Python tree generator syntax or the async syntax, there wasn't really a nice clean way of and then picking it up again, at least that I could find. But like, if you've got a way of doing that, I would love to see it. It would be that would be great if we could take a normal Python program, go and make it run it with these semantics that say, I'm just going to halt execution here and then restart again later. So that's an interesting one to talk to that I'd be keen to. Like I said, it's a bit like an implicit callback. The calling function just says, I need this data. And when the thread that's computing the data finishes, it then restarts the calling thread, the waiting thread. So it's this implicit callback idea. You don't have to do anything; it just happens for you. And there's no event loop. There's no orchestrator that's like controlling all of this and making sure it happens. And the logic there is kind of fairly trivial. I've been talking about a VM, and I've mentioned runtime and kind of handling the glue logic, and it really is a virtual machine on top of Python, written in Python, all Python really easily, and that's great. But it's a virtual machine in the sense that there's a list of instructions, there's a data stack and a call stack, and there's an output model, and there are multiple threads, and there's a memory layer, which means that the threads can communicate with each other. And on AWS, those threads run in separate Lambda instances. Infinite scalability. Neglecting running out of money in your accounts, you get this infinite scalability in terms of compute power, which is great for doing data manipulation. If you've got 1,000 pieces of data, 1,000 chunks that you need to go and process in parallel, well, one option, you go and spin up a cluster. Second option, you do it on your machine and just takes a day. Third option, you use the free tier of AWS Lambda and you do it in a few minutes. When you deploy Teal, I mentioned this briefly, but set of infrastructure that doesn't change after deployment. The logic changes, and the logic is stored in a database, but the infrastructure, like the hardware, doesn't change. Everything else is done by software. These three core Lambda interfaces that get deployed, and there's a data store. There's a whole lot of detail here that we're not going to cover at all. But essentially, you can talk to your Teal instance through this control API and deploy it and see what's happening and get logs, and that's great. New Teal sessions, and I've implemented 3 triggers that I wanted that were useful for me. But there's this API, and then there's the runtime, which lets you talk to everything else that's in your AWS account, and you can modify that runtime configuration. There's a lot of really, really great libraries that I'll just mention because they're awesome and made a lot of this really easy that I would have taken months otherwise. So these are great. Of course, to run on top of a VM, you need some kind of compiler to create the bytecode for the VM. And this is a very, very like standard thing. This isn't particularly, we're taking Teal code, we're transforming it into an executable. And the interesting thing is the optimized bit in the middle, where the compiler could have the option of modifying what infrastructure gets created. So if our code says this function needs to run really fast and it needs to respond within 20 milliseconds, and it needs the compiler can then say, okay, well, I'll optimize for that, and maybe I'll change the way that the function gets called, or I'll change the way that it gets run in the AWS environment. So the compiler can kind of start optimizing our runtime logic. Good. Again, a lot of great libraries, really, really useful. Okay. What did we want? Well, the top three we've got. So we can use Python, we can import our Python functions, and we can call them just as they are and just pass variables to and from them. Great. In that we can run TL functions locally, and there's no simulated environment there. It's all in memory. It's all really fast because there's no simulation involved. And different on AWS, there's a compiler bug. So great, we've got that. Contextual debugging, we've talked about already. We've got that. Good. Operational support is like it's partially there. It's not great. It needs a lot more work. Things like dashboards showing the health of your kind of the stuff that you would imagine. The kinds of dashboards that you see on projects like Airflow and great dashboards showing you the state of everything. I just haven't had time to do that yet. It's totally feasible to now go and implement a TL backend for GCP or for Kubernetes, for example, passing data between Kubernetes nodes. That's totally possible. And once you've written your TL function or TL program, it can then go and run on any of those platforms, and it should run the same, assuming you've configured your environment the same, obviously, but should be the same. Some of the limitations that I think we'll always have in these kinds of systems is by bandwidth, and that's bandwidth in the sense of how much data can we get from the CPU to memory, to RAM. There's a physical link there, and that's always been a problem with computer design. It's always going to be a hard problem for computer science. How do we? So fine, that's an engineering problem. And cost. These things are just going to go down. So as more serverless cloud providers enter the market, like that has to just go down. So fine, great. And potentially some others that if you go and spin up a recursive function that goes and calls like 2,000 lambdas. So there are some differences in the way that we think about programming that will have to be applied to this, and we have to be a bit more careful because it has a much more real impact on how much we're spending. But that's fine. I hope that, I guess it's pretty obvious that I'm quite excited to see how the cloud's going to change in the next couple of years, and how we can kind of go beyond infrastructure from where we are now and think more about the software and not just the infrastructure, but actually what our logic is doing and what our applications are doing. And that is that.
Okay.
Change back to. All right.
So thank you for your talk. It was very, very interesting. I enjoyed the live coding.
Stop presenting.
I always enjoyed the live coding demo.
Live coding is so stressful.
Yeah. Yeah, it rarely works, but it worked this time, which is nice.
It worked this time. Yeah, that's a good thing.
Yeah, always a good thing. So I would welcome any questions from our attendees, and in the meantime, I have a few of my own.
Bring them on.
So one thing that you highlighted was that you can't really use Python directly Python for that to kind of substitute TL. I mean, you can call Python functions within TL, and you can do all that. I was thinking maybe it's a stupid idea, but what if there was let's say some way to mark Python functions that you would like to call within TL, and to have some sort of a reverse translator that transfers Python into TL code, executable TL code, which then
exactly
again will be translated into something else. But
that's exactly it. So like you could decorate, or you could you could wrap some Python functions somehow, and then you could you'd have to come up with some syntax, maybe a bit like PyMC3 does it, where there's like some special syntax and operator overloads and things to signify passing data around into Teal bytecode. Yeah, maybe it is possible. I couldn't figure out. I didn't have like a nice, I couldn't come up with a nice way of, if that makes sense. So yeah, I would love for someone to come up with a nice way of making it from within Python. That would be cool. But like personally, like when I look at the way that some of these other frameworks do it, I don't like having to change. If I want to do a function call, I just want to do a function call. I don't want to have to wrap it in some like, F call X, Y. I just want to do X bracket Y.
Yeah.
Does that make sense?
Well, fair enough.
It's really interesting though.
One thing that I'm kind of new for the whole serverless thing, so I'm not sure. Maybe I'm a bit misguided in my question, but you demonstrated that you could use Teal for, let's say, an API call. You can spin up an endpoint which can be called from a different application, but then it's slow because it takes some time for the to kind of spin up the Lambda and call this. My question would be, which is the slow bit? Is this just Amazon slowly rolling up instances, or?
Good question. No, this is absolutely 100% my fault. Lambda.
Okay.
AWS Lambda is really fast, but to make it fast, you have to organization, or the general advice is that you don't put large Lambda, which is exactly what I've done, because there's this like container startup time of memory, then it takes longer to start up. So that so there's quite a lot of, it takes a little while to start up as well. So that's mostly where the time is, and I'm sure that it can be optimized to reduce that.
Okay, that's fair enough.
APIs at the moment because I'm more interested in data pipelines.
Yeah, that's fair. Okay, so for the time being, we don't have any questions, but if someone would like to ask a follow-up question, they can join in our discussion afterwards, or they can just
totally
write it again in the chat, and I'll cycle back to this later. But besides that, it's a very cool project. I like the idea of having this kind of setup for AWS. I kind of feel, because I've been dealing with AWS for a while too, that you kind of need something else on top of AWS to make it work. There's always, for all kinds of bits and pieces, there is a different wrapper that just does it in a more convenient way. Not sure. I would blame Amazon, but that's just my my take on this.
Yeah, I think the technology is changing so much, and it's going to change again for at least a couple of years. Yeah.
All right, and thank you again. And I would like to call Volko to kind of start preparing or start his presentation.
Yeah, cool.
I'm ready.
Okay, you're ready. Nice. Then if you can share your screen.
Okay, just at the moment.
Yep.
Do you see the presentation?
Yep.
Okay. Today I will talk about compact surjective encoding autoencoder for unsupervised novelty detection. Quite a complex name, but I will show you what it is, and it is very simple. The problem. Imagine that you are in the office or some other place, and you have a task to differentiate between both squares and some other forms of geometric forms. And you build a detector. Maybe you use CNN, autoencoder, or some other neural network. And you have correct data, in-class data, as I will refer to it later, and out-class data. You train the detector to show 1 when you have in-class data and 0 when you have out-class data. And you train, maybe several hours, several days, and you're ready. And then when this detector is in production, you've stumbled on the following problem. Somewhere in the input, somehow you got an image. It is square, it is a blue of ocean, but it's not blue square. But your detector, because it never have seen such a thing, think it's blue square. Fair enough. And if you have the blue square, if the blue square is slightly tilted, the detector maybe will be confused and say that this is not a blue square, which is quite a problem. Everybody in office will tell you that the AI is meme, that you will never ever overcome or will be better than a human brain, or other mean things. But fortunately, we have a solution. We have two main solutions: density function and reconstruction-based approach. The density function is basically some probabilistic formula that will try to match our in-class and out-class data. We send a query to this function, and if the query have a high probability, most likely this query is in-class object. And if this query have low probability, this class this sample is out-class. Is in the out-class. On the reconstruction-based approach, we have usually an autoencoder encoder in the most common way, but also we may have a PCI or other mean to reconstruct the data. The basic idea here is that we represent the input in some latent space, and after that we try to reconstruct from this latent space into the original object. Because we have, when we train this reconstruction-based approach, we will have the knowledge only of the in-class data, and if we try to reconstruct out-of-class data, we will get something that is not very similar to the input. So far, so good, but we still have a problem. It's not always guaranteed to have a good reconstruction because of the dimensionality. Anyway, the basic problem is that we have very few samples very far apart between one another. And loss function for the in-class data or out-class data, I mean, reconstruction maybe will be very small. This is part of adversarial attack or out-of-class classification attack or other types of attack on the neural network that are common in the literature. This is basically the most common approach for the reconstruction-based solution. Here we have here we have the input data, and here have the reconstruction data, and this is the autoencoder with the latent space. and the encoder and the decoder. Basically, when we try to reconstruct the object through the latent space with the decoder, we get some distortion from the main input, and the comparator test if this distortion is too big. If this distortion is too big, the comparator will tell us that this is out of class data. If the distortion is very small, it will tell us that this is in class data. But how to tackle these two problems, which are very big problems for this type of classification? And in order to solve this, we will have the following things: compact surjective encoding autoencoder. Basically, this method combines autoencoder with the GAN. It do this by several steps, which I will cover later. But basically, on the first thing that it will do is to try to represent the encoding class, encoding samples, into a small manifold in the latent space. Also, it will enforce the latent space to be every point in the latent space to be reconstructed again into some kind of input in class data. And we use some layers of the GAN in later to aid our task. The main here is the architecture and the solution. It maybe looks complex at first glance, but it's really not very complex. First, the first thing that we will need to do is to try to make the following formula. First, we need to constrain the input into the manifold by using this statement. And after that, we will try to reconstruct the data using this statement here. Of course, this will be not perfect because of the reconstruction error, but we will try our best. For every input data, we try to reconstruct it correctly. But what happens on practice? When we try to reconstruct out-of-class data, or to encode out-of-class data, we will get the loss will be very similar to the input data, to the in-class data. Here's the latent layer for the autoencoder for the input and out from the in-class and out-class data. As we can see here, in the in-class data latent layer, the layer is very sparse. This is because of the surjective property, which we will discuss later, of the neural network. And here we have the out-of-class data, which is a little bit blurred, but still in very much the same space as the in-class data, which is a problem for now. Okay, what we will do first? In order to enforce the encoder to only encode in the manifold, which is in our case is it's 2D hypercube. between 1 and 0 in order to get into the activation space in the layers. We use the following clauses under statement 3. As you may be familiar, this is a very famous formula for the GAN networks. Here we have the discriminator in the DZ words. Here we have the encoder with the in-class sample, and we have ZI, which is basically uniform sample from the manifold, which will be hard-coded in order for the encoder to can encode it and to be surjective. Basically, we will try to this was here is for this part here, which is basically, and this is our discriminator. This constrains our encoder in-class and out-class data into some small manifold, which when we define it here. Of course, when we constrain the input data, we will constrain in-class data. We will constrain the out-class data also, which is not a very good solution, but we will try. This will be demonstrated later. Basically, okay, we have now constrained the input data, in-class data, into this small manifold. What we will do next? Next, in order to make the autoencoder surjective and to try to reconstruct to make the input to be surjective with respect to the latent layer, we use a second discriminator, a second GAN network, which is described here, which you use only the latent space and the generator, the decoder, which is a G. G is our decoder here. And basically this is this step here. Here is our the discriminator. Here is our decoder, and here is our input space. And what this was do is to constrain the latent space to be in some to be surjective with respect to the input data into in-class data, which is fine. We have constrained in some way from the encoder, and so far so good. But here is where it become interesting. Basically, we have several problems at this point. The GAN network has its problem also, and unfortunately, it brings its problem into this network, as well as are there its advantages. Basically, we have a collapse of the wide latent representation because of this constraint here, because the GAN network have a problem with the copies of the representation because of the sparse data, and also we have the problem with the high dimensionality of the input data. And what we do, basically, this is one of the most genius part of this paper. Basically, constrains the discriminator and the decoder and encoder, the autoencoder, with respect not to the input, but with respect to the latent representation, which we can see here. This is some samples from the input representation, and here you have the inversing the encoder from the inside out. Okay. Basically, at this point, the encoder is in this shape. This is the decoder, this is the encoder, and this was traced to train the encoder and the decoder with respect to the white space, not the input space, with respect to the white space. This is in order to mitigate this latent representation co-ops, which is a very out-of-the-box thinking when we think that we usually try to adjust the decoder and the encoder with respect to the input data. The only thing that we have done so far with respect to the latent representation is with the variable autoencoder. Which is generative basically generative autoencoder. So also we have one other trick in order to constrain the input space is this basically to use FL, which is basically a hidden feature map of this discriminator here. We use this in order to constrain our reconstruction of the image, to have a better reconstruction. And thanks to these two layers, to this feature map, we did at one point we enhance our reconstruction of the input data on the in-class data, and we did iterate the reconstruction of the output of the out-class data, which is a very interesting property, because when we first tried to make our detector, we have input and output, in-class data and out-class data, and this paper, what is telling us is that we need only in-class data. We don't need this out-class data, basically, because we will learn our discriminator only on the features of the input data, on the in-class data. And this at the same time, we exploit the property that the neural network is not aware of what is known and what it is not known. for the neural network, everything's just a giant matrix operation, basically. And here we can see also that the surjective property, that when we try to encode this data with our in-class data, because we have only trained the discriminator on in-class data, this discriminator will reproduce our in-class data correctly, and we will fail to reproduce our out-class data correctly because it simply never have seen such a thing at this point. I will basically fail at the reconstruction of the data, which is a very interesting property. Because as I have said previously, this the property of the encoder to encode basically in-class and out-class data in the same space is generally a bad thing. But here we have we deteriorate the decoding of the latent space. Basically, as this is our encoder and this is our decoder, and this is our latent space. If we have in-class data here, we have a good, somewhat good encoding here with the surjective property of this discriminator here. And we have also somewhat similar encoding with the out-class data here, thanks to this surjective property, which is a weakness. But the interesting part comes here at the decoding phase here. Basically, when we try to reconstruct the data with the respect to the decoder, everything's almost fine. We still have some glitches here and there, but mostly will be fine, thanks to this discriminator here. But when we try to reconstruct the out-of-class data, everything will be distorted because simply this discriminator, the feature maps of this discriminator here are not have never seen something like this before. They simply never have seen the features of the out-class data here, which is great. We have just cut our input data in half, and at the same time we have covered almost every single case of the out-class data, which is a very genius thing, at least for me. Here's the end game of the basic of this encoder decoder. Here we have the surjective property of the encoder. In basically this tells every in-class data must be encoded to some specific latent representation, or to be encoded in some space in the manifold, which is the latent representation. This tells us that every latent representation must be basically correctly reconstructed at the decoder. This here is basically this regularization here that combat the co-ops of the latent representation. And this is also some this is also some property to regulates the reconstruction of the data, basically here. And what we have at the end of this big neural network. Here's some results of the reconstruction of the out-class and in-class data. Sorry for the bad quality of the image, but this is the best thing I have. Here we try to reconstruct to detect only tricks. And here we have in-class data and out-class data. Here the in-class data input. And here's the output of the same in-class data at the end of the autoencoder. And we can see that the reconstruction here, and here's very somewhat good. It's not perfect, but it's good. But when we try to reconstruct some out-class data like airplanes here and here, or horses, or other objects, or cats, or any other objects, we have deterioration of the reconstruction. Basically, thanks to this GAN network, this discriminative network, because simply the discriminative network have only seen the input, the features of the in-class data, and haven't seen the features of the output data. And this this feature map, this discrimination, this GAN does not know how to make something for the latent representation of the object. And we can use this additionally, this latent this GAN network in order to classify to separate linearly the input and output, class respectively, with the feature maps of this discriminator here. Basically, we can see how good we can discriminate, how good can reconstruct the data, the input data and the output data, basically, and tell us is this reconstruction good enough. Also, this this metric is not very good. Thus, you introduce some kind of cosine representation in order to get the additional features from for the classification. But this is also good, a really good metric, basically. And here we can compare the input, the original data with respect to the generated data thanks to this discriminator here, and tell us, is this good reconstruction or this is better reconstruction, basically. And that's about it, I think.
Okay. Thank you for your talk. It was very detailed in their implementation. Again, I invite everyone who has any questions to ask them either in YouTube or on Slido. And until that point, I have a few. I'm not sure whether it's a question, but more of a remark first. Can you share any details on how this was evaluated in the paper? I'm asking because it's not unheard of to have a model operating on a dataset with a very large class imbalance, such as this case, to have some flows that are very easily exposed by an external dataset. That's why I would be very interested to see how this was evaluated.
Yes, basically, actually, in the results here, you can see that we have a slight problem with the respect to the car here. As you can see, the reconstruction of the car here and here is somewhat good. This is basically because the features of the car and the truck are very similar, and this is a problem, of course. Also, it's not always problem like here, which is always it is also car, but thanks to the fact that it's pictured from the above, it can separate it linearly. But yes, it's the biggest weakness of this in-class and of this autoencoder is when we have similar features of the in-class and out-class data. We have a problem thanks to this GAN network. Because then this GAN network will almost successfully reconstruct the input data thanks to the similar features which is trained on.
Okay, and my next question was, do you know if anyone has tried to use similar models for some outlier detection or out-of-domain detection in let's say in different scenarios, in more real-life setting? I'm not sure what would be the correct setup for images, but probably there is something.
Well, also there is papers with similar that have traced similar things, like just check to check the name, like OTC GAN. But this paper haven't touched of the subject of the surjective really, which is basically this thing here, and this discriminator here. The surjective properties is when the input data have at least one point to be represented into the outclass into the latent space here. And so we have a PCA when we try to encode the input data across some line in the space, or when we have multiple higher dimensions space with the PCA. So of course there's also a problem with some exception with when there is a data point that is far at some dimension, at some axis of the dimension. This is a problem with the PCA. Yes.
Okay. All right. So if anyone has any questions to either of the speakers, I invite you to join our discussions afterwards. And now, before I'll end the stream, I would like to thank again everyone for coming, and especially the speakers for preparing and presenting these wonderful talks. So right now, I'm going to share the link to the chat room in the YouTube chat. So anyone who'd like to join the discussion afterwards or want to share some interesting idea or even propose a suggestion for a talk for next time, please do join. And for the time being, I'm stopping the stream.